dozen instruments on Cassini, a dozen remote sensing and in situ instruments on Cassini, and another half dozen on the Huygens probe shown here. Cassini for scale, you can see, oops, where's the pointer? There's a desk here. So Cassini was a good-sized spacecraft. And as I said, it spent a long time in the Saturnian system, and this plot over here that's very busy shows all of the orbits that Cassini did at Saturn. So you can see it changed inclination to be able to look down on the poles, to be able to look at things within the ring plane, and you can see just how much time and how much exploration it did in the system. During this time, there were actually 126 close Titan flybys, which sounds like a lot, and it was a lot. It was a lot to plan, but Titan is a really complex system, and the number of questions we still have about Titan after 126 flybys is daunting. So Cassini had a number of instruments that were designed specifically to be able to explore Titan as a system, to understand its surface, to see what's beneath the haze in the Titan atmosphere. The cameras, the imaging science subsystem here, were designed with a filter, a specific narrow band filter out here at 938 nanometers in one of the gaps, one of the windows in the methane absorption spectrum, and this allowed us to see the surface. So this is what Titan looks like in kind of real color, what our eyes would see, and this is what you can see if you actually start looking out into the infrared. Not only did Cassini have infrared filters on the camera system, which revealed the surface in all its glory, there was a visual and infrared mapping spectrometer that actually was sensitive out to 5 microns, so much longer than the wavelengths our eyes could detect. So Titan is limited. You can't get a full spectrum from orbit because you have these you have to see the surface in windows in the methane, and so that's what these gray bars are. So there were several windows down to the surface spectrally, and using those, the VIMS instrument was able to build up a map of the surface as well. So this shows us the variability of materials on the surface, and this is designed. This is an enhanced color view designed to bring out these differences. What we don't know is the detailed composition of these different materials. We know there's a lot of organic material on the surface. We know there's organic material mixed with water ice, but we don't know the detailed compositions and the distributions. But we know the distributions, we just don't know what they are. Cassini also had a synthetic aperture radar, had a radar instrument, had multiple modes, including altimetry, as well as synthetic aperture radar. And so what you see here in these noodles, these strips, are ground tracks built up by SAR imaging during any given flyby. So we've Cassini imaged several tens of percent of the surface with the radar, as well as the global imaging in the near infrared. So a few other facts about Titan. I showed you the size of Titan compared to the other satellites in the solar system, compared to our moon and planets. The surface gravity on Titan is about a seventh that of the gravity here on Earth, because it's a smaller moon. And as I said, the atmospheric pressure is about 1.5 times the pressure here. The surface temperature out in the outer solar system is not high. The surface temperature on Titan is 94 Kelvin, or minus 290 Fahrenheit. And at these temperatures, the bedrock composition is water ice. So Titan, the system on Titan is composed of very different materials than we're used to here on Earth. We're used to water ice, but the interplay of these materials, the water ice here isn't rock, the liquid water here on Earth isn't lava. And so it's a very different set of materials acting on Titan. Beneath the surface, there's also a liquid water ocean. There's a deep liquid water ocean in the well beneath the surface. So it is among the ocean worlds in the outer solar system. As we've learned over the last few decades, many of the icy satellites in the solar system have oceans in their interiors, and that's another reason that they're particularly interesting targets. So this is what Titan looks like in the near infrared. Or if you're down beneath the haze, you'd also be able to see this. So you can see there are a lot of dark regions about the equator, and then there are dark regions at the poles. More at the North Pole than at the South Pole, which is particularly interesting. There's a little one here. Not terribly little, actually. It's about 200 kilometers across. So we've been seeing these features on Titan for, since the 90s. We've been observing them, but we didn't know what they were. We didn't know what landforms there were making up these features. You can see a few that are familiar, right? There's an impact crater here. There's an impact crater here. There's one there. But like Earth, there are not a lot of impact craters, which is intriguing, because the reason there aren't a lot of impact craters on the surface of Earth compared to the moon or other bodies in the solar system suggests that there's a fairly young crater retention age, and that there's active geologic processes erasing the craters. But if you look at this, like many bodies in the outer solar system, nothing jumps out as an obvious pattern in terms of the geology. So the vast equatorial region, those dark regions around the equator of Titan, turn out to be the biggest Zen gardens in the solar system. They're giant seas of longitudinal dunes that wrap all the way around, almost all the way around Titan's equator, except for this bright feature, which is that same bright feature we saw in the early imaging from HST and Keck, it's called Xanadu, and it's a very different geologic feature. But all of these dark areas around the equator are these seas of sand dunes. And what's fascinating is that these sand dunes, the sand on Titan, which is about the same size as sand on Earth, the sand on Titan is organic. We don't know how the sand particles form. We don't know if it's aggregated aerosols from the atmosphere that somehow grow, that there's some process that lets them grow to be large enough to be sand-sized particles that can saltate on the surface of Titan. It's not. It's organic. It's organic material. It may be organic material mixed with water ice. On Earth, sand is broken down. It's eroded from the bedrock, the silicate bedrock. On Titan, perhaps the sand is eroded from the water ice bedrock. But somehow those sand grains have to get covered in organic material because they're not water ice. So this is one of the mysteries we still have about Titan, is how you form the sand on Titan. Nonetheless, there are these spectacular fields of longitudinal dunes on the surface. And this type of dune is one that is less familiar perhaps to us. It forms in a regime where you have the wind coming from one direction primarily in another direction. And so the sand is actually migrating longitudinally along the dune. There are a few places on Earth where we have analogs. Namibia, there's some excellent analogs for longitudinal dunes, and there are some in the desert southwest as well. But it's a fascinating process and something that is so familiar and yet composed of completely alien materials to us. So I mentioned there are a few impact craters, so you can see some of them here. This one is about 80 kilometers across. This one's a little larger. The impact craters have a similar progression to what we would expect. This is the largest one, which is about 400 kilometers across. They have a similar progression to what we expect in terms of the morphology, the shape of the impact craters that we see with this progression you see with size on other bodies. But you can see, especially in this case, how degraded, there's sand dunes forming here near the ring here, and you can see that the rim is cut in places. It's very similar to the types of degradation we have here on Earth. There are also some mountainous areas. This is the Mithra Montes, which is about 11,000 feet high in one of the maximum height in this area. Is that you can see there are three ranges here that parallel each other. The tectonics of Titan are not well understood. And this is another area where there are tectonic features, or presumably tectonically uplifted mountains. Again, you can see the complex interplay of the geology. This is very like Earth, where you have all of these different geologic processes overprinting each other, which is fascinating, but makes it much harder to understand the geology. And of course, here on Earth, we can go out into the field and we can do subsurface sounding and we can get information to put together that puzzle. But on Titan, we're right now just looking down at the surface. And so teasing out all these relationships is fascinating. There are hints of cryovolcanism. Cryovolcanism is cold volcanism, volcanism wherein the lava, in the case of Titan, would be water ice, not water ice, water, or perhaps a water-ammonia mixture. And this data here, this is a combination of the radar data. So you see the dunes here in the radar data, and these three stripes along here are just seams in the radar data. But this has been combined with the VIMS spectral information. And so you can see that there's a feature here and a potentially flow-like feature here. This looks very similar to the morphology of volcanic features on Earth.